Okay, we can start. Today, we are very happy to have Quentin from LBNL. He will tell us about the productivity bound on nonlinear supersymmetry in the blackboard. Let's welcome.
Thank you, Dan. So thanks for having me today. Thanks everyone for being here. Yeah, I'll discuss this positivity bounds on nonlinear supersymmetry, which is based on that paper out early summer last year with Gabriele Casagrande and Emilian Dudas, both at in École Polytechnique in Paris. So let me start with a few motivations for why we're doing this. So probably the first motivation is that people observed, okay, let me just say also that I'm going to say some words in those motivations which I'll come back to in the rest of the talk, so don't panic if some of them are not well defined. So people observed in inflationary backgrounds that there can be issues associated to gravitational propagation, in particular causality issues. So you could have gravitini that go faster than the speed of light in inflationary background, leading to the usual paradoxes associated to the loss of causality in those spacetimes, or in those situations. And that happened in a precise case, which I will make precise not now, but later on. It only happened for some effective descriptions of the gravitational topping. In particular, those EFT descriptions have to do with the constrained superfields. I'll go back to this later on during the talk. So this, for instance, I won't write references too much, but I'll just write initials. I apologize. So, this was found, for instance, in the paper of Kolb, Long, and McDonough in 2021, and papers of Dudas, Garcia, Mondrini, Olive, Peroso, and Werner in 21. And that kind of issues associated to gravitational propagation were reminiscent of something else, which is that some of those EFT descriptions, which again I will try to describe later on in the talk, had no known UV completion. Of those EFT descriptions. So this, for instance, was discussed in papers of Dargata, Dudas, and Farkos. 2016, right? And so when you put the two together, namely the lack of UV completion and problem with speeds of particles which are larger than the speed of light, this suggests that you could study the positivity bounds. So again, these things I will clarify in what comes, but for those of you who may know about the different kind of topics, that probably indeed makes sense to relate the three kind of topics together. And what was interesting in that precise case is that those positivity bounds, which are bound on some coefficients of EFT operators, I'll describe them in a moment, it's interesting to try to see how they are, what's their interplay with theories which are structured. So for instance, if you have some symmetry or some assumptions you make on your EFT that correlates different operators, you may wonder how the bounds relate, the bounds which apply on some subset of the operators, what do they translate to when you have a theory where the structure is such that those dimension 8 would be, for instance, fully determined at dimension 4 coordinates or dimension 6 coordinates. So this I will very vaguely describe as positivity bound with structure. I'll try to make that more precise in the following. Okay, so that were our motivation, trying to understand these two problems and connect them in terms of positivity bounds. Good. Okay.
So you are not going to talk about dispersion relations to put the bound on the coefficient?
I'll do this in a short way. Yeah.
Sorry?
So I'll mention that.
Okay, sure, okay.
So I'll review all these things later on. Just so you know where I go. There will be a bit. I will discuss a bit of loss of causality, a bit of UV completing EFT, and a bit of positivity bounds, which are all connected, as I'll try to argue. Okay, so there's no question on this. I'll start by some rather long introduction on nonlinear supersymmetry. So one uses nonlinear supersymmetry whenever one wants to have an effective description of a theory that undergoes spontaneous supersymmetry breaking. So it's the low energy description of spontaneous SUSY breaking. And that is meant to be quite generic, namely and when you just want to have such a description, there's like a whole zoo of possibility. Namely, you can have an arbitrary set of fields. They don't have to be arranged in multiplets, but there are in principle one clear-cut prediction of this, which is one Goldstino. So the Goldstino is the Goldstone fermion of the spontaneous breaking of supersymmetry. So that's basically the only clear-cut prediction. The rest is that this Goldstino can interact with any kind of matter. This description you can also see in the context of gravitational, you can also embed this in gravitational theory, in which case that Goldstino will be determined by the gravitino to form its longitudinal degree of freedom. But in some context, for instance, when the gravitino is very light and it couples to matter at very high energies, for instance, this description is sufficient to capture, for instance, the interaction of the longitudinal degree of freedom of the gravitino with matter. Okay, so these descriptions are quite useful. For instance, at least they're used a lot, let's say. They're used in cosmology, for instance, when you want to describe the inflation in terms of a full, having in mind that there is supersymmetry in the deep UV, and you want to describe the inflation that couples the inflaton to gravitons, but also to gravitinos, but you don't want to have a full-fledged model of a supersymmetric model. In that case, then you want to rely on an effective description of that sort that couples the light stuff that is predicted by supersymmetry breaking to your inflaton. That has been done extensively in the last 10 years or so. You can also use this kind of description to try to parameterize what could be the first, what could be, for instance, the interaction of a light gravitino to the standard model in the limit of very heavy superpartners. And this kind of description also shows up at the very fundamental level in string effective field theories, where you have broken supersymmetry, for instance. So in string theory, the bright supersymmetry already at the string scale, or at a higher scale than the one we usually think of, then one ends up with a parameterization of that sort, where the supersymmetry is spontaneously broken. You have that kind of spectrum. You mean not things that don't belong to supersymmetric multiplets, but that talk to massless Goldstino or to massive gravitino in the limit, where you reinstate gravity. Good. Okay, so how do those theories look like? You may be familiar with the coset construction of Coleman, West, and Zumino. So for that theory, this I'm not going to review, but it's a very systematic procedure of building the EFTs of spontaneous symmetry breaking. So how Goldstone bosons interact with the light matter fields after a theory undergoes a phase of spontaneous symmetry breaking. So there is a very similar approach to this, which you can work out. And this results in the so-called standard description of supersymmetry breaking that was worked out by Volkov and Akulov in 1973. This results in a description where you have a Goldstino field, so it's a spin half field, and its variation, its supersymmetry variation, is not relating itself to a boson like you would in usual supersymmetry, but it relates the Goldstino to a composite operator of itself. So there is a shift in the beginning. So this is a dimension 2 object. That's the parameter that parameterizes the supersymmetry transformation. So that would be the transformation related to that parameter of supersymmetry. So there's a shift, which is very reminiscent of the Goldstone boson shift, and then that's not enough. You need something a bit more involved to really get back to the algebra of supersymmetry, which looks like this. Where I will be using two component notations for the fermions. So that transformation in itself suffices to realize the supersymmetry algebra. So you can take, for instance, commutator of that transformation, and you will land on translations. That everything you expect for the supersymmetry algebra. It's just that it's nonlinear. Maybe there's a shift, and there's no, and this shift allows us not to have any boson partner of that Goldstino. The picture being that those heavy partners might be decoupled and become heavy when the spontaneous symmetry happens. And there's also a way of embedding matter field in this. I'll probably get it wrong because I didn't write it down. But some matter field instead of being related. So that can be anything. Could be a fermion. Could be a boson. Doesn't have to be related to a fermion of half integer spin difference. But to an expression of that sort. So you'll get something like this. I'll probably get the sign wrong. But I'll have to express this. Some transformation of that sort around the Lorentz limit. So the claim is that similar to the coset construction, any kind of description of nonlinear supersymmetry should match to a description in terms of these kinds of constituents. So that's quite of an old story. Okay, and then of course the goal is similar to the question you may ask when you have Goldstone bosons is what kind of actions can they build which are invariant under that transformation and coupled with these different fields. So again, there's a systematic procedure for doing so, and that was worked out in those papers and follow-ups from other authors. So that's kind of the old approach, I would say, to this nonlinear supersymmetry. And a bit more recently was So there are other approaches to this, including one which was revived quite recently because it's very simple to handle and it matches very fast to things that one finds in textbooks for supersymmetry, which have to do with the constraint superfields.
By Cyborg?
Yes.
By Cyborg. I mean, constraint superfield is by Cyborg.
Right. So okay, so no, actually it's much older than this, I think. But so this thing, as you said, right? I think the first time that this appeared was a paper by Roche in '78.
Oh, okay.
And indeed, this was like revived, I think, and led to a second bloom of that discussion, following the paper of Komarkotsky and Cyber in 2009, which is probably the thing you had in mind here. So these constraint superfields allow, well, they are not telling they are telling the same story in a different fashion. Namely, they will discuss the same kind of spectra, namely a Goldstino, which is a clear-cut prediction again, and any kind of matter, not falling into any kind of multiplets. But it will try to do so by matching to the kind of actions you would write in a regular supersymmetric model, where the supersymmetry matches bosons and fermions, and there's no shift like this, and the gravitino is massless, etc. In order to do so, you do something like you would do if you try to write a textbook and explain how you go from the linear to the nonlinear sigma model. So here you would get for instance, some complex field phi, or not necessarily complex, some field phi with a rotation symmetry on it. That would get you there, and here you would like to parameterize the dynamics of the Goldstone bosons that you match. So a quick way of doing this, right, is to simply fix that object to its value. So here you have an action phi, and here you can, at low energies, you have basically all the degrees of freedom in that guy except the radial mode. So you can, and this you can impose, you can encode by this kind of field constraint. So here, okay, I should probably take a transpose to match the nonlinear sigma model of textbooks. So what you can do is simply take the same action, right, and write the action that arises once you impose that constraint. You can solve that constraint, determine how many free field that leaves, you plug the resulting expression in this, and you'll get the leading order expression for the interaction of the Goldstones that show up when you do that, when that symmetry breaking happens. And of course, this coset construction would not care about that part of the picture. It would simply very systematically write what could have happened anyway, But here you kind of see the result of that procedure emerging from directly matching from the theory you have in the UV. So something a bit similar can be done in supersymmetry. Namely, you can keep the supersymmetric action you know in the UV, which is written using superfields, and simply impose superfield constraints now, and plug them directly into the action that you would have written in the UV. So that thing was, as I say, described first in that paper, but made systematic, I think, in that one. So I will follow. I will briefly review how these guys do it here. So for instance, you could wonder, how do I get in that picture? So for instance, you could do this, right, with a single two-component field, and get one Goldstone out by breaking the symmetry of this two-component field. And so you may wonder, how do I get the theory of a single Goldstino in that kind of picture? So what you can do is to start from a field X. What these people showed, what Komarkovsky and Seidler showed, is that you can get the same result by starting from a Caro superfield. Maybe I should briefly review what Caro superfields are. Let me do a very fascinating review of supersymmetry, which will be very unsatisfactory to explore. But so one way of writing the supersymmetric action. One way of building the supersymmetric action is to enlarge the space-time coordinates into a larger set, where you add to them two anti-commuting variables, which are Majorana fermions, was this here. And now a field which would only depend on the space-time coordinates is upgraded into a superfield. An object which depends on all these variables. And now, to build an action, instead of integrating over d for x, you're also going to integrate over d for x and these two-component objects of some new Lagrangian density of these objects. Okay, that doesn't tell you much, but that's what I'm going to stick with. So the superfields are those objects. And those objects, just let me say something. An example of such an object is an object that has a scalar. So these things are anti-commuting, so you can expand them. You can perform the Taylor expansion of those things, and this thing will truncate, simply for the reason that you cannot have an arbitrarily high operator in terms of fermions. So this thing, for instance, can be expanded. It will have one. So there's normalization. There will be one scalar here, one fermion here, and another scalar. So for instance, that's the kind of expansion. So these objects will have these fields, which are space-time fields, and some expansion along those coordinates. Okay. So I will refer to that kind of description later on. So here, you will see this kind of expansion. So space-time fields, and an expansion along those extra superspace coordinates. Okay, sorry, that's probably a bit too fast and incomplete, but that at least gives a picture of the language I'm going to use. Right, so here you can start with a field of that sort. So in that paper, they argued that one can start from a Carroll superfield, so a superfield that has really that kind of expansion in the boson, fermion boson, and simply impose some kind of constraint to describe the spontaneous breaking of supersymmetry. And the constraint these people introduced is that constraint, this quadratic constraint, which does not imply that x is 0, because x has that complicated expansion in terms of the superspace coordinate, and those things square to 0. So there's of course a trivial solution to this, which is that x is 0, but there are non-trivial solutions to this. And the trivial solution to this, the non-trivial solution to this would be that the scalar which I wrote on the left, as the first component of this, is constrained in terms of, sorry, let me put my Goldstino here, is constrained in terms of the fermion. So that shows us that indeed spontaneously is nonlinearly alive in that description, because we had a description in the UV that had as many fermions and bosons. That's what happens in those supersymmetric actions. The dynamical bosons are as many as the dynamical fermions. when I impose that constraint, I lose my bosons. So I have a description, which is only in terms of the fermion, and I separate my multiplet, very similar to what happens here. Nevertheless, I still retain a perfectly exact supersymmetry in the IR. It simply becomes nonlinear. Namely, it takes a form of, it takes that kind of form. Namely, it does not mix boson and fermions anymore, and there is one particle that shifts. And this G is given the same name as this one because that's essentially the same particle. And here you can write the action of that object and just export it to the IR and just plugging in the solution of that constraint in that action to get a Goldstino, an action, so that only depends on that field F here, G here. That field F is not dynamical and can be integrated out. When you do this, and you do the appropriate set of field definitions, you can land exactly on that description. So yeah, so those authors showed that this kind of approach is essentially equivalent to the theory of, well, it's exactly equivalent, sorry, to the theory of Goldstini that these people worked out much earlier.
So I'm trying to remember, is it right that the chiral constraint implies that capital F is independent of X? Something should imply that, right?
No, it doesn't. Actually, it has an expansion. Right, okay, let me...
so F is also given by an infinite expansion in terms of G?
Absolutely, yeah. This big F.
And that comes from the same x squared equals 0 constraint?
No, that thing comes from the action you're allowed to write. So this action, in principle, would be... right, so here, in principle, you have to plan a polynomial in terms of different fields, right? And but when you use the usual rules for building supersymmetric actions, and you check what term
this is the usual thing. F is auxiliary, so it's depending on what action you write, F will be given by.
Yeah. So the action of that guy looks like x dagger integrated over the 4 theta's.
Okay, yeah.
Plus 1 f integrating over 2 theta's. Okay, so let me write it better.
Yeah.
Basically, that description leaves out a unique action that is such that this f is fixed to something that will produce that whole thing. So this f here will be a parameter of the action. Let me write it down. To get the sorry, I'll continue this exercise. To get the Volta-Fakula theory, one just needs to start from L of x, which is integral over d for theta of x star plus integral over d2 theta of f plus hash. Yeah, so that thing will fix that thing is the most complicated action you can think of given that constraint, which works with the precept of how you should write actions in supersymmetry. And that thing will fix this F field and be related to this little f here, which is now the parameter of the action. Sorry.
Yeah, so is theta a fermionic field?
So theta is not a field, it doesn't depend on x, it's a new coordinate. It's a trick, if you want, it's a trick I use to expand, to write the supersymmetric action in a very concise fashion. So this I don't have time to review, but you don't have to, you can write the supersymmetric action without ever referring to that object, but it's quite convenient to have to think about fields in this extended superspace.
But you also have some like anti-community so that the expansion truncate at
exactly,
squared?
Yeah.
Exactly. So
See, that cube becomes 0.
In principle,
cube becomes 0.
Yeah,
cube
is 0.
You can have like twice that one and twice that one at most.
They're spinners, they're Weyl spinners, so that's why they're two-component spinners, so you can have theta squared, but any higher powers will vanish. They're Grassmann.
That's I'm sorry, I don't have time to review these really, but as you see, you can think about them as a trick to have a very compact repackaging of the different fields you need to write this supersymmetric action. So there are finitely many of them which are contracted with an appropriate power of the superspace coordinate. Good. So does that help? Thanks. Right, so this thing would be completely equivalent to the theory of a single Goldstino, which is of course expected because this paper showed that thing is the most general thing you could ever expect. So it's consistent. And now you can ask, how do I get matter couplings in addition to this? So now I argued that you can describe the Goldstino by just plugging into the naive UV action some constraint. But I should also have a way of doing this that gives me enough freedom so that I can choose the matter I have in the deep IR. Namely, the supersymmetry. The breaking of supersymmetry would break the multiplets into pieces, and some of them will remain light, some of them will become heavy. So there must be a way of extending that formalism to account for this. And this and the same kind of tricks can be used, namely using multiplets that look like the one that have that realize supersymmetry in the usual way, that have as many bosons and fermions together. You can use the same for the matter field and impose a constraint that would remove the part of the spectrum you don't want. So, for instance, if you want no scalar, if you just want the fermion, you can impose something like this. Where that object is very similar, is exactly similar to this one, with just new fields at each of those positions. And similarly to the result, here this constraint was imposing that the leading scalar in X has to be expressed in terms of fermions. This kind of constraint does something similar. Maybe it removes the scalar which sits in that guy and expresses it in terms of the fermions that remain in the spectrum, the one here and the one here. So here one had, for instance, in that case, for just the usual case of the nonlinear sigma model, one can see that kind of constraints arising simply from the dynamics of that object. Namely, you can work out the potential, and you see that at the minimum you have to impose this thing, which is simply the fact that this field is getting its sped. So you may ask, okay, what about these things, right? Why are you imposing this? Is it something I see realized from the UV? So if you start from that field, you cook the model in a way that spontaneous supersymmetry breaking happens. Will you see this arising, for instance? And the answer is yes, almost. So for instance, okay, this can be done by writing an appropriate action for that field here. For instance, that one here can also be seen if you write a something of that sort. If you write something of that sort in the UV, with the cutoff here, an operator of that sort in the UV would do two things, right? It would would give a mass to the scalar in that object. And it's consistent with the fact that when you plug the effect of that operator in the equations of motion, and you take the decoupling limit where that object becomes much more massive than the energy scales that you want to consider, then the effective description reduces to this. So that kind of effective description can be given a UV description in terms of operators that give the appropriate mass to the field you want to decouple.
Sorry, I have a question for this x phi equals 0. How this one we tell you the scalar part of phi is heavy.
Exactly. Yeah.
What about the other case, like the fermion part of the phi?
Okay, I'll come to this.
Okay, good.
Yeah. Sorry, yeah. So I just wanted to say that in some cases we understand exactly what happens. For example, this operator gives a mass to the scalar and matches to that description.
Okay.
So that description seems like the natural thing to do if you want to describe a fermion, a scalar getting a mass. But indeed, you can ask something similar with the fermion, right? So if you want now an IR scalar, you want to write constraint of that sort that would now remove the fermion. And people have thought about the following constraint. So here, let me add some item here in the list of supersymmetric things that I'm not reviewing properly. But so there, in this space, as much as you can have a space-time derivative, you can in that superspace introduce space-time derivative, like larger kind of derivatives. So So you can, there's like a preferred notion of derivative in that space, the space-time derivative, and two kinds of derivatives, which are almost like differentiating with respect to that guy, plus some nonlinear terms in addition. But roughly, to understand what I'm saying, it's enough to think about that guy as just the derivative along that direction of the field. There are some pieces to it. There are usually pieces to it, but to understand what this thing is doing, that is enough. And so you can impose a constraint of that form. So imposing a constraint of that form would put to zero the linear piece in theta bar, which happens to be proportional to the fermion in here. So okay, this you have to trust me if you've never done this computation. It's a bit of algebra in the superfield, but that's what happens. So this thing will decouple the fermion in that object and express it in terms of the scalar here and the Goldstino here. The problem of this, yeah, and now we can find the kind of problems which arise, which I tried to advertise in the second point on these motivations, which is that then there's a whole zoo of such constraints, and some of them are a bit mysterious from the point of view of the UV. Namely the thing which I sketched just before, namely that you can write effective operators that would match onto that description. Well, for the fermions, that's not that easy. People have tried to look for this and failed. Namely, you can try to write UV actions that would give a mass to the fermions, and to get really that constraint, what you want to write, well, it is weird. It has like higher. It has derivative of the kind we want to see. It may have ghosts, and yeah, it's yeah. The origin of those constraints is a bit was a bit unclear. For instance, there was a second kind of constraint that people advertised, which is very similar to the first one, but does something a bit different. So, for instance, these two things could remove again that yeah doesn't. Yeah, so this is bigger. So these two constraints would do something equivalent. Maybe they would remove the fermion in that field, but they would do it in a qualitatively different fashion. So, for instance, if you took those two descriptions and you send them into a UV Lagrangian that has both x and this field phi, you will get slightly different results. So, for instance, you wouldn't get the same scalar potential. So, if you wrote the same action with the same fields with those two different constraints, you would get the same dynamical fields, but not quite the same interactions. You wouldn't get the same scalar potential, and crucially, you wouldn't get the same high mass dimension EFT operators that couple the scalar to the Goldstino, which will be the focus in the short while. Yeah, so trying to understand which of those constraints is the right one, and how it relates to UV, just matching to the UV, remains an open question.
Sorry, so the statement is that either of these constraints defines a multiplet that has just an IR scalar.
Absolutely, yeah.
So naively, I would say, fine, you can use either one of them, and any Lagrangian you can write in terms of one should be equivalent to the other with some complicated field redefinition.
Right. No, yeah, okay, that is correct. That's something I'm going to get to.
Yeah, so
I think the question, please.
Yeah, but then what is the question? I mean, if they're equivalent in that sense, then the question is what is the question?
That's right. Okay, so another question. With that, very good. So that's this is definitely correct, and that's something I wanted to say at some point. Anticipating on that. So the right question becomes how should you use them? So for instance, in that naive picture where you take the UV Lagrangian and you just plug the constraint in, which of the two does the job? Because indeed they will be related by Schroeder definitions, as they must, because they are individually related to that unique description. So they are all related to that description, so there is a way of going from there to there and back to there, so therefore there's a connection between the two. But when you do these manipulations, if you start with, let's say, constraint A that you plug into the UV Lagrangian, the resulting expression using constraint B will not be the UV Lagrangian anymore.
Sure. I mean, they're only equivalent if you include all possible terms.
Absolutely.
Right?
Yeah.
So if you have a particular set of terms, of course, they will give you something different.
That's right. Okay. So let me to motivate why I'm asking the question, let me come back to that first point here. Yeah, the question was that now you want to do something useful with those, right? You want to choose a constraint, plug them into the simplest Lagrangian you can think of, and just work out dynamics of the system. And what has been done in the literature so far is to use either of the two and plug them in the same Lagrangian. And when you do this, you get, in some cases, wrong answers or appropriate answers. Which you can, so you get in the form of those issues, right? So some of those constraints will lead to those issues. Some of them, well, one of those constraints will lead to that issues, and the other one will not, given the same UV Lagrangian that you use for the two. Right? And our work was mostly trying to differentiate which one you should use, given like some
Well, why should,
fundamental principle.
in general, it is not correct to plug either of those things into a UV Lagrangian.
That's right.
There's no reason, I mean, you have to match, and the matching would be different for these two.
Yeah, that's absolutely correct. I'm just saying that that's not how people have been using those constraints.
Okay.
I agree with you, yeah. I agree with you that should be the conservative thing to do, but that's not how. So what people have done in the literature is to take those constraints and plug them into a simple Lagrangian of that sort. So polynomial expansion of, well, something
So the
that
fact that if you plug some of these things into some Lagrangians and get superluminal propagation tells you that there are positivity constraints, right, on the most general couplings, because you've shown that you can violate them, right? You can violate the positivity bounds. You can violate, there's some regions of parameter space that are not allowed by superluminality. So is the idea that you're going to more systematically find the allowed parameter space for the low energy effective theory? Is that what you're trying to do?
Yeah, what I'm trying to do is to, the goal is not probably a bit less ambitious than what you have in mind, namely that I have a set of constraints, which was like given in that kind of catalog, right, where people said, okay, here's an appropriate way of doing it. And so, so that first restricts the problem, right, because there's a zoo of possibilities, a finite set of possibilities that you can select, right? And among these different possibilities, I will just argue that some of them are preferred. I'm not going to try to list all possible constraints and choose and find like a unified, but I'm not going to work out a unified criterion that you should apply in your constraint in order to test how you should use it, right? I'm just going to start from some constraints, for example those two, and determine which one is correct.
Okay, why don't you go on and we can discuss further. Yeah.
Good. Okay, so what has been done? So the mindset is the following. I was going to say, what has been done in the literature for when people wanted to just, for instance, like describe inflation in supergravity when supersymmetry is broken, right? Was to start from a Lagrangian of Goldstinos and some matter field, let me just take one, right? And apply some constraints to get rid of the different degrees of freedom that would complicate the analysis of inflation that you may want to carry on this. So, but okay, the starting point is the same Lagrangian in the UV, and for instance, imposing this or imposing this. And it turned out that the result here is fine, namely that this issue does not arise. And here you have the gravitino speed can be double. Okay. So yeah, this, as you said, right, is something that is, so that there is a relation that is well known, which is that these kind of of behaviors which you can then like design. Given that kind of behavior, you can choose a background on which you see a clear causality. I mean, you can send signals back in time once you have this superluminal propagation. And these things were known to be correlated with something that's called positivity that I'm going to review. And that was the work, well, that's I think quite old school physics, but it was again revived in the work of Adams, Ahmed, Dubovsky, Nicolis, and Rattazzi in 2006. So that part of the story, the fact that you can send in general background where signals like will propagate backwards in time. This thing, well, okay, that would be the picture, and that is related to that keyword, and that keyword is a different picture. The keyword are sign constraints on EFT operators. So that thing, the claim is that that kind of behavior will happen precisely when some EFT operators will have the wrong sign, and the wrong being something very, very clean that you can work out in the EFT description. So I'm not going to review the connection. I can just explain very briefly how that positivity is worked out. So the canonical example would be a Lagrangian that has a d5, a d mu phi to the 4 coupling. The claim of positivity is really like simple given the name, which is that coefficient should be positive. Okay, that I'm not sure I got the sign right, but okay, there's a choice that in which case C is very positive, unambiguously. Hence the name positivity. When you start like making the theory more complicated, you add more fields, you have fields with different spins, then the content of positivity becomes a bit more complicated, but the picture is the same. And the reason behind that kind of constraints is that you can compute scattering amplitudes in this EFT. Starting with you can compute the 2 to 2 scattering amplitude of phi. And on that scattering amplitude, you know a lot of things. You know its analytic properties, you know that it must satisfy unitarity, you know that it must satisfy crossing symmetries and so on. So there are many theoretical constraints on that amplitude. And those constraints extend beyond the region where the EFT is valid. So there is a whole theory, right, thanks to which you can compute the scattering amplitude. At low energy, that scattering amplitude will be captured by the EFT description. At high energy, it will not be. But the like, structural properties of the amplitude will remain correct everywhere in parameter space. Will remain identical. Sorry. So in particular, you will have like, for instance, scattering on the poles. You will have a factorization on lower point amplitudes and so on. That will be true everywhere. So that allows you to use these dispersion relations kind of arguments. So the idea is to consider the amplitude in a larger, well, you can complexify the difference momenta. For instance, you can assign the Mandelstam variable S a complex value and study the amplitude of, you can study the continuation of the amplitude to that complex space. And the statement of analyticity, for instance, will tell you that if you write it, well, will allow you to use complex analysis of analytic functions on that amplitude. So for instance, if you compute a contour residue, a contour integral of that sort, so integral of the contour of A, well, you can deform that contour and send it to infinity as long as you don't hit some singularities of that amplitude. And the singularities would be on the real axis, and there would be either some kind of branch cuts at loop level or simply some kind of poles if you're at tree level. But, so the result is that you can take that contour and deform it as long as you avoid any kind of singularity. And if your amplitude is well behaved, or if you chose to divide here by sufficiently many power of S, then that big circle vanishes, and you only pick up what's left on this axis. And what's left on this axis you understand quite well, in particular that what's left on the axis related to the cross section. And this, to make that connection, you need to invoke the unitarity of this amplitude that you know at all scales, not only at low scales where the EFT is varied, but also that we postulate all the way to the highest possible scale. Okay, I'm not going to go further in the discussion, but there's a clean way of getting those bounds. The nice thing of those bounds, right, is that here I was arguing that you get issues, but those issues, if you want to see them, you have to go to, well, people went to inflation, they and they consider the gravitino propagating, they have to solve the equations of motion and so on, consider this for different inflation background. So it seems like a very, well, it seems like first a very precise setup, and second it seems like a complicated thing to do. But those kind of positivity, they don't have, well, you can work them out in flat space. It's a very, like, it's a simple statement at the level of 2-to-2 scattering amplitudes. And so it's nice if you can reduce that problem simply to that positivity, because then you can diagnose where the problem lies in a much simpler fashion. So that's what we did. And yeah, so that's what we did. And so this very simple picture of the 2-to scattering of scalar, as I said, can be exported and also applies to any kind of theory. So you can compute the 2-to scattering amplitude in any kind of theory. In particular, you can compute it in those theories. So here, there's a Goldstino that is inherent to the description throughout. And given those descriptions, we argued that there is also a scalar. So you can compute a bunch of scattering amplitudes, but it turns out that the one that had, so 4 Goldstinos, and the one that had two Goldstinos with 2 scalars. So that's my scalar. Yeah. Those scattering amplitudes are sufficient to see the problem. So yeah, that's really a simple object, right? It's a 2-to-2 scattering amplitude in flat space. There's no gravity, there's no inflation or anything, but it's a very simple object that you can compute given those constraints and given the Lagrangian. And if you apply the positivity bounds to that specific case, I'm not going to give them into details because they're a bit more complicated because the fermions have helicities and here there are different kinds of particles. But the result is simply that they match exactly to the kind of things you want to impose, as expected, I guess. If you compute those bounds in that setup, they match exactly to the constraints that make that issue disappear, and they simply become trivial in that description. So those positivity bounds in that description with that kind of constraints are trivial. They need out the form something positive should be positive, right? So like a perfect square should be positive, for instance. So they are trivial. And here you get something different. You get something should be larger than something, which is not automatic. And so there in those theories there is the room for violation of positivity, which is in one-to-one correspondent to those issues. Which is, as I said, expected from the experts would have expected this, I guess, because there is a known relation, as I said, because between those our causality and positivity. It's nice. It's something we recover exactly. And it's something which is nice because it's very simple to do. You have like these 2-to scattering amplitudes to compute, and you get the same conditions that the ones you would get from this complicated inflation analysis.
Sorry, before we go on. For the 2 constraints, what's the equation motion for the fermion, for the heavy fermion? Are they the same for equation motion?
You mean? Okay, so here I'm removing the fermion. You mean if what is the result of that constraint?
Yeah. What's the solution to that constraint?
Oh, it's a big mess.
It's very.
It's ugly.
I'm thinking the following question. Suppose you have a UV model, right? Yeah. You have SUSY breaking. Then the scalar component of the chiral field obtain a mass, right? In that particular UV model, you can try and integrate the scalar by equation motion, right?
Yes.
In just one. So I'm thinking which one gives the correct equation motion for a particular UV model? Have you checked all that?
Yeah. So if you choose a particular UV model, you can. Okay, it's okay. That was supposed to be the next part. Maybe I'll come to. Okay, let me come to this in a sec.
Oh.
It's not that trivial because in the usual way of working out the supersymmetric actions, you will first fix to their on-shell values these objects, the auxiliary fields. Right, so they will.
But I can first let's say if I UV model. Can I first using equation motion to eliminate the f first, then Is it possible? So
Which one did you say? So
I was trying to say.
What is, so for instance, if you want, okay, so if you want to determine what is heavy, for instance,
Yeah.
you need to, in principle, you need to first determine what this is, right? So this will tell you which fields, so this will determine, for instance, the scalar potential. And in a description of that sort, where the scalar has to be heavy, then you must enforce that this field will achieve this. I mean that these kind of fields will create a scalar potential which is consistent with the fact that the scalar is light. You see what I mean?
Sorry, I thought we are into out the fermion. Sorry.
Absolutely, but I'm just saying that from the equations of motion,
Yeah.
There is no obvious limit that decouples only the fermion and not the. Sorry. Yeah, there is an obvious limit that decouples the fermion, but it's not obvious that this thing will also not decouple the scalar. So what you want to ensure is that the limit you're taking does not decouple the scalar.
Okay.
And that thing is not obvious if you try. Well, if you only try to send a parameter in the equation of motion that will decouple that guy, which is doable, if you fix everything else, you will also send the scalar. Well, you also decouple the scalar. So there's some kind of tuning to perform if you want the scalar to remain light. And that tuning is usually performed by working out, well, this tuning becomes manifest when you work out the equation of motion of that object. You see what I mean? So, and those constraints kind of skip that part. In that constraint, you keep the auxiliary field, for instance. In that constraint, the auxiliary field is fixed, but to something which is not in its equation of motion, which is something that does not depend on the equation of motion. So, right, those constraints do not depend on dynamics at all. So they don't exactly align with the thing you would do in your given model in order to fix the scalar, to tune the mass of the scalar to 0, let's say.
You mean the two constraints, the one which is fine, the constraint which is fine, will give you same as equation motion, the result that will give you.
That's right.
If the one is not something else, in the addition to equation motion. Am I correct?
For given Lagrange, yes.
I have to answer this question.
Okay, I would have said yes and no. Should I keep on answering this? Okay, let me go ahead and
continue.
Let me continue. Right, okay. Okay, the only thing I wanted to say is that there is a fast way of getting, if you're interested in inflation or something that uses these constraints, and you want to be, and you're worried because people in intricate settings found some issues, I think it's nice to know that there is a very fast way, very fast procedure of checking whether you're fine or not, which is to compute this positive results. But they map to exactly, that they will tell you whether or not you have to worry about this, which I think is nice. Okay, and so that's all I wanted to say about the positivity bounds. Sorry, that's, again, I'm happy to give more details offline on how you get those, how they look like. I just want to stress just once more that there are just two tools scattering in flat space, and that's an easy thing to do. Once given the fact that people already worked out, of course, what the bounds are. So, for instance, there is a paper of Pellatini in 2016, and there's a paper of Clement and Navrod in, I don't have the name, probably 19. Sorry, this is correct. So people have worked out the bounds in the general theory of the fermion and the scalar, so you can just take the results and check what happens given your two scattering amplitude. So it's a very fast process. Good. And okay, what I wanted to address next is connected to the question of Dan, namely, how do we see this whole thing arising from matching? Namely, as we discussed, right, this thing that people have been doing indeed may not be, well, is likely to be incorrect in most cases. And what we wanted to see is how bad it is in either of the two cases. Namely, is there a piece that we can see we are obviously missing when we use either that description or that description? And by doing this, we try to match a generic UV action with just two derivatives in the UV, a supersymmetric action. We try to match it to those descriptions and see in which case we are obviously making a mistake. And the motivation so there's one tricky thing when you want to do this, which is that, as I said, right, in principle, when you want to work out the dynamics, the mass eigenstates, blah, 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 of a given supersymmetric theory, you have the two dynamical fields which are here, and that guy here is non-dynamical. It's needed to write the supersymmetric action in a very compact fashion, and to have the supersymmetry algebra closed off shell, but it's not driving any dynamics. So usually you just first integrate out these guys and work out the interaction with those fields. When we impose these constraints, we do something a bit different. Namely, we get rid of some fields, but these constraints do not depend on the action. Whereas the way we would get rid of that f term here depends on the action. So there must be a way of integrating out the different fields, which is not the usual thing. Usually you would just like fix this to the equation of motion, and for instance, integrate out this when this is heavy. So not this, because here that's the Goldstinos, but another Fermion, another multiplet of that. So if we want to match, we have to design a way of doing this that allows us to, for instance, only integrate this thing out, leaving this fixed. Well, leaving this free, leaving this still off shell. And to do this, we can rely on the intuition that when we have nonlinear supersymmetry, we can really break multiplets into pieces. As I tried to argue, I think what used to be here before, when you have these nonlinear realizations and symmetries, for instance, you can, like the different matter fields have no reason to lie in multiplets.
I'm just not quite clear what question you're asking here. So,
which
by matching, normally
okay.
what I understand by that is I have some UV theory, and then I'm trying to find the effective theory that matches onto that. So,
right. Yeah.
So you have a particular UV theory, and you're trying to find out how to express that theory in both of these different formalisms, or could you just?
Right. So okay, I'm going to do something.
Yeah.
So thanks. Yeah, I'm going to do something slightly like this. I'm not going to work out the full EFT you get. I just want to have. Okay, My goal is simply to differentiate between these kind of constraints. So here, I should say that I'm showing two kind of constraints, but there's a whole set of things that have a similar behavior. Namely, you could remove, for instance. That removes the fermion. You could remove like a fermion and half of the scalar to get a real scalar. I think that there are many options, and in all of those cases, there are possibilities which are fine and possibilities which are not. Okay, so here I'm going to discuss only those two things and just saying that it's like a more general procedure. So what I want to do in that case is to write a generic UV action, and I will engineer a way of getting rid of some of the components. And I will work out the very leading pieces to the EFT. So I'm not going to work out the full EFT. I'll take the decoupling limit. I will just show that in those two cases, in that case, I get nothing in addition to the nice matching, and I will get something non-decoupling in that case. That's my goal. My goal is to show that if you start from a UV action, you impose the constraint. It's not the same as matching, integrating out the thing you try to remove with the constraint. So with this constraint, you remove the fermion.
But I mean, if one of these, you already applied the same procedure and found that one of them, at least you found that the two cases are different.
Yeah.
So obviously, at most one of them, I guess I'm just not sure so what can I conclude from that I can't already conclude? That, I mean, you've already showed.
Oh, right.
Applying these same two constraints to the same action gives you two different things, and in fact, for some choice of that action, one of them has an inconsistency.
Yeah.
So what's the additional thing that we're learning now? I'm sorry, I'm not understanding.
Yeah. So if the question is just like you have two options and you want to get rid of one, we're not learning more than this. I agree. What I wanted to argue is that what I wanted to exhibit is how you can do this matching in a way that makes this kind of constraint appear. So,
I mean, I have to say, I just have an overall issue with this, which is that, as I said, it seems to me that these two constraints are different low-energy, nonlinear realizations.
That's right.
And you should be able to express any Lagrangian in terms of either one.
That's
And
right.
so there's nothing preferred about one compared to the other, except that it might be a little bit easier to use one
No, that's
compared to the other.
absolutely right.
But there's no physics in just one or the other constraint.
No, I agree with you. Yeah, the
The
physics.
way that you match would be very different.
Yeah.
So in that context, I'm trying to understand maybe you should just go on. But
Yeah,
I'm just telling you, it's not clear to me right now what you're doing.
I agree. I understand. Sorry. Yeah. So. Right. So in terms of physics, the physics is in the choice of these two things at the same time. Right? So there's one constraint, which is one choice.
But the correct matching would not be, I mean, what this shows is that the correct matching would not be
I agree.
just imposing the constraint.
That's
It
right.
cannot be that.
No,
It
that's
would
right.
have to be actually matching physical things.
That's absolutely right.
And then you would get the same low energy theory from the same UV theory.
That's
Then they would both be fine, presumably they'd both be fine, because presumably your UV theory makes sense.
That's right. Okay. So. Yeah. The goal. Okay. Okay. Let me.
I mean, you can just go on, I'm just, maybe it'll become more clear.
No, it's absolutely right. Sorry. The thing maybe I haven't stressed enough is that the way people have used this constraint is really a bottom-up picture, right? So you make a choice. You make a choice.
You convinced me that the way people did it was wrong. You convinced me of that.
Yeah. Okay. So the next thing you could ask, right, is then what should people do? Let's say, okay, one thing which is nice about that constraint is that it's much simpler than that constraint to use. So the question would be, can you save it, right? Can you still use that thing that people like and people have started manipulating and just modify the starting point to get back on your feet, right? Still in that perspective where people want to be bottom up. So you choose a light spectrum, you impose that you want to use supergravity, and that forces you to use this kind of description. So there are, right? You could just say, okay, let's use that guy. It looks more consistent from the beginning, right? At least it passes the constraint. At least plugging it into a UV erosion seems to be a sensible thing to do. And just abandon this one, or you could also say, okay, I want to keep that one, I prefer it for some reason, because it's easier to solve, for instance. Can I work out what I should modify in here to make the thing land back on its feet, on its feet again? And that's what we are trying to do by matching. So we wanted to start from a given theory, the UV, and create an object that verifies that constraint, and addition on that part. Which in practice is what you said, but it's implementing the different, well, it's implementing what happens when you match that constraint through field definitions. That will implement this. Yeah, the way I wanted to discuss this is that it's not trivial to, well, the way we usually do matching in these supersymmetric theories, well, sorry, the way we would do matching in that case is not landing on that kind of description that keeps the superfield description intact, right? So I'm not cutting. Here I still have superfields. I still have objects which live in superspace and so on, which is not what I would get if I naively integrated this out. Like I would have gotten rid of my auxiliary fields, for instance, which I would have to put back by hand and recreate the EFT. Right. Okay, let me just say it very fast. I think that way. Then I probably should stop. Okay, so we start from an action of that sort, where this is constrained in the usual fashion, but this is unconstrained. And we want to integrate the objects that leave only the degrees of freedom described by that constraint, and we want to see what, in addition, will show up in this dimension once we match. So the way to do this is to realize that we found a way of doing this, which uses the nonlinear supersymmetry encoded by that guy, which allows us to cut this multiplet into pieces. So for instance, something which you can do is to take the superfield and cut it into two pieces. The pieces that I will call F plus the rest. So I'm still talking about superfields here. And that thing I would define to be a very ugly expression that does what I want, which is this. So bit ugly, but it does something very clear. It extracts the auxiliary field in that object. So for instance, so that object is a superfield, which is fully determined by a single boson, which is the auxiliary field, that F here, which lies in this object. And so there's no fermion, there's no scalar, there's no dynamical fermion, there's no dynamical scalar anymore in the description. And I can iterate this. I can now take that procedure, that part here has no auxiliary field, but it has a single dynamical scalar and a single dynamical fermion. Just the full superfield is really described by two objects. There's no such thing as an extra F here. And I can iterate. I can create phi fermion and phi scalar, which are, I'm not going to write down because they're ugly, but we have explicit formula. So I can cut, by explicit formula of that sort, I can cut that superfield into three different superfields, which capture independently the three objects which appear here. Which is expected because we know that once we have nonlinear supersymmetry, once supersymmetry is broken, there's no reason that the multiplier should be in a given object. And now I can integrate out everything but the scalar. So now that I have three different superfields, I can write the equation of motion for these two guys and leave that guy out. And the funny thing about that guy here, the good thing about this is that this thing happens to verify exactly that constraint. So I can cut my superfield into three pieces, which I'm happy to show you explicitly if you want, but they're ugly, in a way where this thing, right, my original superfield, which has these three different components, will be a sum of these three, and this one, which is the only one that has light particles in it, will verify that constraint. So now I can work out the equation of motion of these things. They are really ugly. I'm not going to write it down. And you get a very ugly expression out, but explicit, that tells you exactly what you should add in addition to this. And the result, sorry, I can write the result just to show it explicitly. Sorry, it's not particularly enlightening, but so the effective Lagrangian that you get, if you get rid of these two things, if you land on the left equation here, would be the original Lagrangian, in which you plug the constraint, plus a horrible piece, which I'm just going to write. So there's something like this. So that's the Keller potential that you would have in that object. Something like this. And a big parenthesis. This being the superpotential plus a mess that I'm not going to write. So you can work out what the matching generates here in addition. And there's nothing that can be sent to. I mean, there's nothing that decouples of this. This is like an addition in the EFT once you send all large mass scales to infinity. So it's not something that will decouple when you look at the lowest energies. At least it will not decouple more than the Goldstinos will decouple. And if instead of integrating out those two guys, you decided to keep these two here, and you're just integrating out this here, this whole thing would drop. And the effective action, so in that case, this whole thing would disappear. And which is consistent with the fact that together, these two guys, they amount to that constraint here. Right, so this I think is an explicit way of showing why why that happened, right? So you're getting some causality or some breakdown of positivity in the left-hand side of the description because you're missing this full non-decoupling piece that you can work on. So then now if you're a bottom-up physicist and you want to use either of the constraints, you have two choices, right? Either you take this one, which is arguably simpler in terms of resolution, but you have to account for this whole big mess to match to a UV description, which, okay, there are more pieces to the right than to the right, which make this really ugly. Or you have to use that one, which is arguably a bit harder to solve, but allows you to simply plug the constraint in and not bother with this whole thing. Yeah, so that helps.
Why don't you wrap up and we can have some discussion
Okay.
afterwards.
Okay, so let me wrap up fast. Sorry, probably way for time. Okay, so yeah, the thing I wanted to convey 3 points. I think the first is that these positivity bounds are the appropriate technique to know when or you will run into these computations, and you should probably run them before you go into like inflation and so on, because they're much simpler and they allow you to check very fast if your starting point is inconsistent. One thing. Second, yeah, right. Something I briefly mentioned here is this positivity bound structure. So I wanted to just so that whole discussion is nice in my opinion because it has so these constraints they like, when you solve them you have a full expansion, right? You solve for instance here you solve the Fermat in terms of the scalar and the Goldstino and derivative of the scalar and so on. So even if you start with the two derivative action, this kind of constraint and the structure of nonlinear supersymmetry correlates, like for instance the scalar potential with super high terms in derivatives. So you may end up with bounds on the scalar potential, for instance, due to the dimension 8 coefficients because of the structure of nonlinear supersymmetry. That correlates these different things. And the third thing, the third thing would be this kind of construction, which I think are new. I've never seen them before, which is the explicit. Well, you can explicitly use nonlinear supersymmetry to navigate between the different kinds of constraints and implement at the superfield level this separation of the different pieces of multiplet that you know must exist based on the structure of based on the theory of nonlinear supersymmetry. Yeah, I think I'll stop here. Thank you.
Thank you. Question. Max.
Questions from someone who's not.
Yeah.
I've asked a lot of questions, so
instead of breaking it up into phi f, phi psi, phi s, if I just wrote out the component fields in the UV Lagrangian and integrated out the component that I wanted to get rid of, isn't that equivalent and simpler? Or
So okay, sure. This you can do, but then if you want to match to a description of that sort that uses the full superspace, well then you have to once you have your low energy description, you have to reinstate the observation to go back to description in superspace of a fully offset multiplet, for instance. Sorry. Okay. No, sorry. Okay. Well, sorry. Simpler. Right. You have a component action, which now you have to repackage into a superspace action. And
well, if supersymmetry is broken, why do I need to write it in superspace?
What's nice about this superspace thing is that you know by construction that supersymmetry, despite broken, is exact. Despite being broken, is exact. If you start with the component description, you need to build Lagrangians, which are invariant under the nonlinear supersymmetry, which is okay. There are techniques for this.
I'm saying, starting with the UV Lagrangian, which is supersymmetric.
Yeah. Oh.
Write it in components, integrate out the heavy fields, then I think I'm done.
Oh no, obviously, if you want to match, if you want to describe a given UV physics, of course, but here those things are used in the bottom-up picture, right? You say, I want to define in inflation, what people do is, I want to describe an inflaton, sorry, and I want the inflatino or the synclaton, and how do I do this? And how I want to be quite generic, so I don't want to commit to using a given UV model, but still I want that spectrum. How do I do that? And people do this in this, at least in the recent years, people have done it in this way. Maybe they have chosen the spectrum, imposed the constraint that must correspond to that spectrum, but still those constraints being expressed in superspace, you know by construction that supersymmetry is broken, but still it's potentially broken, but exact. So the action you write has immediately the broken supersymmetry, the exact broken supersymmetry that you want.
But I think that you haven't been, so bottom-up, I'm a big fan of bottom-up physics, but if you're using a bottom-up effective Lagrangian, you should write down the most general thing that you can write down. And evidently, this procedure is not giving you the most general thing.
That's right.
So let me just ask, is it known in this language what the most general, in either of these languages, you pick which one, if I want to make a scalar coupled to nonlinear supersymmetry, is it known how to get the most general low energy effective Lagrangian?
Good. So, sorry, when you said pick either of the two, so in the old Volcker
You pick one, just pick one.
So which one? You mean the constraints?
You pick. Pick one of them.
So those constraints, you mean, right?
Yeah.
Okay.
I'll pick the one, if you ask me to pick, I'll pick the one on the left. Is it known how to
No.
write?
No, it wasn't. So what people?
But is it now known how to write down, and I repeat, the most general,
Yeah.
low energy theory? Is it known how to write down the most general low energy theory using that language or not? Are the rules known?
I would say better known.
I think using his approach, I believe if I understand correctly, you're adding one piece. I think he's trying to claim this is the most general
Yeah. So
Lagrangian
So,
paradigm.
for
that piece, yes,
example,
but
you
I'm
can
not-
tell me that you should start with the most general thing that is a function of x and phi.
Respect supersymmetry.
That not only respects supersymmetry, but is local in superspace. What do I mean? That expression right there may be local, I hope it is, otherwise it's wrong, but it's certainly not local in superspace, because it has superspace
Absolutely.
derivatives.
Yeah.
So, for example, you might say the answer is, oh, you start with the most general L of x and phi that is local in superspace, and then you imply, but the most general one, not just some one term that people like for some silly reason,
Yeah.
but just the most general thing, and then you apply the constraint on the left, and you are guaranteed that you have the most general low energy effective Lagrangian. That would be a possible answer.
No. I think the right one give you the possible answer.
That's what you said is correct for that constraint, but definitely
For
not
this
for
one,
that
the answer is not known.
Yeah.
For that one, the answer is known. No.
You plus something else
that,
term.
that approach you can systematize, right? So what we worked out is just the non-decoupling piece. I haven't worked out the correction in 1 over the mass of the fermion. And I suspect that there will be like infinite.
So it's known how to do it for the thing on the right, but what you're doing is you're trying to figure out
Yeah.
how to translate that into the language on the left.
Yeah,
Yeah,
exactly.
okay. We
Yeah.
haven't tried to do that.
Okay.
Our point was mostly to argue that we should use that one, but yeah. what we found is it also allows us to do what you just said, yeah. But the leading expression is already very, as you said, right? It's clearly non-local in superspace. It happens to be local in space-time, yes, absolutely.
I mean,
And I haven't tried to work out that.
usually if you have choices on how to parameterize a low energy theory, a very important requirement is that you do know how to write down the most general term. If you don't, you probably, it's hard to imagine what it could be good for if you don't know how to do that.
No, I absolutely agree with this. I think, our work was trying to clarify this kind of aspects, absolutely. Yeah. No, that's absolutely right. Yeah.
Can I ask, a physics question? Because, one of the things that I didn't know before I came and listened to your talk is that if I write down some theory with some matter fields and nonlinearly realized supersymmetry, there are some positivity constraints, okay, on the amplitudes, and therefore some positivity constraints on the coefficients. Now, something I think would be particularly interesting is that, if I told you I have the standard model, and I now want to couple, make it, nonlinear realized supersymmetry, at lowest order in the derivatives, the interactions that the Goldstino has to have with the standard model particles are completely determined. Okay.
Mm-hmm.
Now I have some freedom at higher orders. I also have some freedom at higher orders in the Goldstino self-couplings, right? I have some freedom at higher orders in the derivative expansion. But it would be extremely interesting to know if there are any constraints on the MSSM or higher dimension operators that come from the consistency of their couplings to Goldstinos.
Oh,
And if those go beyond the ones that are known already, there are some positivity constraints that are known, right, in the, actually for the standard model and dimension 6, I'm not sure that there's anything known. Starting at dimension 8, there's some known. But anyway, I'm asking whether these positivity constraints could possibly tell us, under the assumption that making an additional assumption that we must have nonlinearly realized supersymmetry, actually gives us some positivity constraints for the matter self-interactions that don't involve the Goldstino. Is that possible?
So I would, but boy, based on what we saw, I would say no. I mean, in that, if you use that constraint, which from what I said seems to be the right thing to do, because as you said, it allows for local expansion in superspace, right? Then we found like a very trivial answer, right? So there's nothing left. So we for instance, right, as you said, right, in that description, the scalar potential is bounded due to positivity bounds. But that one, as we argued, breaks down. In that case, the scalar potential has nothing to do with the positivity bound. For any scalar potential, I get a completely trivial
So
positivity bound.
in components,
So I would say no.
if I just go into components, and I want to understand on the left what interaction is in components, what interaction is making the gravitino speed superluminal. I guess it's some higher derivative coupling of the Goldstino.
Yeah, it's a dimension 8 thing to the
So
scalar.
so somehow it's something that I secretly have I'm free to choose it. It's not determined by the lowest order couplings, right? Like I said, at lowest derivative order, the couplings of the matter fields to the Goldstinos are completely determined at lowest derivative.
Yeah, absolutely.
But at higher derivative order, I start having freedom.
True, yeah.
So this gravitino speed is, I guess, some higher
Yeah,
derivative
it's
coupling.
dimension 8.
of the-
It's
yeah.
But
Okay.
it's things that contribute to those amplitudes, no?
Yeah, but in particular, higher derivative things that
No,
contribute
absolutely.
to that.
Yeah, that's, yeah.
Right.
No,
I'm
it's-
just
it's-
hoping that somehow you could change, you could say that, some sign for some operator is, which you didn't even, we don't know if we have supersymmetry or not, okay? But if we believe that we did, that we could derive some positivity bounds that, for things that don't involve the gravitino,
Yeah. No, I see
that's
what-
probably impossible.
Yeah.
That would be super cool. But
I see
that's-
what you mean. What we found points in the opposite direction.
Yeah,
I
okay.
mean that there seems to be at least one formulation that trivializes this relation immediately. Yeah. So I would
Okay.
I would doubt it, but okay. I mean, we worked out with like one Goldstino, one Carroll superfield, and maybe now. And okay, we haven't explored, but yeah, something like this seems to work very, very well. I mean, it has nothing non-decoupling. The matching seems to be quite local in superspace.
So so my question was, you said that it's known that the most general thing is to start with local in superspace and then do the right thing, do the thing on the right. Where is that discussed? Is
The
there a
fact that
reference
this
to
should, oh no, I think that's one of our results, and that we should do that. So
Okay.
what people knew, okay, I think the little was known before. I think
Okay, so that's actually
so
yours then.
people had classified cases that had problems, and people had tried to UV complete either of these constraints, and people had problems with this. But the matching thing was not done. Okay, I'm not aware of what everything trying like back in.
I'm saying that you get the most general low energy theory that way. You showed that.
Yeah, so this I think is one of our. I don't think it was. I don't know of any paper that did this.
Okay.
Yeah, probably we can discuss a little bit.
I'm
and
sorry. I'm sorry.
Let's.
Let's.
Okay, thank you, speaker again.
Okay.